Hi everybody, today we're going to talk about operations with matrices. So first, it's really important to see different representations of matrices. So typically the entire matrix can be represented by a capital letter, so this would be matrix A, and it would represent the entire thing. Now you guys also know that you can represent a matrix as a rectangular array of numbers, which we've been working with. Another important thing to know is that you can represent a specific element in a matrix by saying A sub and then having two values. So these two values will represent the row and the column. So A sub 1 1 is column or row 1, column 1. A sub 1 2 is row 1, column 2. So this will always be how we denote a specific element within a matrix. So let's start by talking about the addition of matrices. It's super intuitive. All you have to do is add the corresponding element. So for example, in this first one, I see this is row 1, column 1, row 1, column 1. We add up those two elements. So here we'll get 0, and then we'll add up the 2 and the 3 to get a 5, and then -1. And 3. That's all there is to it. For this one, adding up all the corresponding elements, we get 0, 0, 0. And then for this one, you notice that here we have a 3 by 3, and here we have a 3 by 2. So this column does not have any corresponding elements, which means that we can't add them, and we say that this is undefined. So that's our one restriction, is that the dimensions of the two matrices when you add need to be exactly the same. Okay, now we're going to talk about scalar multiplication of matrices. That's when you're multiplying the entire matrix by a scalar. So you're just literally going to go in and multiply each element by whatever your scalar is. So if we have 3 times matrix A, you just go in and you multiply each element by 3. So we'd have 6, 6, 12, -9, 0, -3, and 6, 3, 6. So just like that. Now, it's the same process, even if you have a combination of scalar multiplication and addition or subtraction. So here you can do this in whatever order you want, if you want to do it all in your head or write out part of it. So let's do it all in our head together. So we're going to have 2 times A and then minus B. So we're going to multiply all of our elements in matrix A times 2 and then subtract the corresponding element from matrix B. So here we have 2 times 2 minus 2. And then we have 2 times 2 minus 0. So we'll have 4 and then 8. And then you keep going from there. So then we'll have -6 minus 1 is -7. And then we'll have 0 minus -4 is +4. And then we'll have -2 minus 3 is -5. And then in the last row, we'll have 4 minus -1, which is 5. And here we'll have 2 minus 3, which is -1. And then we'll have 4 minus 2, which is 2. So the properties of matrix addition and scalar multiplication follow many of the properties that we already know. When you're adding, it doesn't matter which order you do it, doesn't matter how you group it. When you're multiplying by a scalar, you can multiply the scalars first and then multiply it in, or multiply them individually. If you multiply by 1, it stays the same. You can distribute from the left or from the right. So very, very similar properties to just basic algebraic expressions. All right, so now we're going to talk about evaluating an expression. So here there's actually 2 different ways we can go about this. We could take this scalar and distribute it to each matrix, and then we could add it, or we can add the 2 matrices and then multiply it by the scalar. It doesn't matter either way. So let's add them and then multiply. So we're going to do 3 times, and let's add up those scalars. So here we'll have a 2, -2, 7, and 8. And now we're just going to multiply each element. So we have 6, -6, 21, and 24. And like I said, if you would rather distribute in the scalar and then add up the two resulting matrices, you should get the exact same answer. All right, so when we're solving an equation with matrices, so you'll be given what the matrices are, and then it says solve for x. For this problem, it says if 3 times x plus a equals b. So x is actually going to be a matrix. So when we're doing this, we're not going to substitute the matrices in yet. We're actually going to solve this algebraically and then substitute the matrices in. So let's solve for x algebraically. So we can say 3x equals b minus a, and then we could say x will be 1/3 times b minus a. So that's when, at this point, you are going to substitute in your matrices. So b is -3, 4, 2, 1, and then a is 1, -2, 0, 3. And then here you can choose to subtract and then distribute, or distribute then subtract, but either way you should end up with -4/3, 2, 2/3, -2/3. So if you're ever asked to solve an equation, make sure that you do it algebraically with the representations of the matrices and then plug in the matrices once you've already solved for x. All right, so now we're going to talk about matrix multiplication, which is a little bit different. There's a very specific process that we follow. So the first thing to note is that you can't just multiply any two matrices together. They actually have to fit a very specific requirement. So the number of columns in your first matrix must equal the number of rows in your second matrix. So it's really a nice way to set it up is to list the two matrices and list their dimensions. If these two middle numbers are the same, which would be the columns of the first and the rows of the second, you can multiply the two matrices. And it's extra nice doing this because if you take your two remaining numbers, that's going to be the dimensions of your product. So the process of doing it's a little bit easier to show than to write it in words, but essentially you're going to be multiplying the elements of the rows of your first matrix and the columns of your second matrix. So you're going to multiply and then add up those products, and that's going to be your new element. So let's give this a try. Like I said, it's a little bit easier to show than to say how to do it. So the first thing we need to do is check to make sure we can multiply. So this has 3 rows and 2 columns, and this has 2 rows and 2 columns. So since these middle numbers match, we know that we can multiply them, and our product matrix will have a dimension of 3 by 2. So here's how the process works. We'll start by multiplying the terms in this row with the terms in this column, and then taking the sum of those products. So we can do -1 times -3, and then we're going to add it to 3 times -4. So these elements go together, these elements go together, and then you take the sum of those products. So now let's work our way down. Now let's do this row with that same first column. So we can do 4 times -3 plus -2 times -4. And now we can do this row with this column. So 5 times -3 plus 0 times -4. All right, so now we're going to do that same process. We're going to go rows, but now we're going to multiply and add with the second column. So do red, with red. So -1 times 2 plus 3 times 1. And now we'll do blue with blue. So 4 times 2 plus -2 times 1. And then we'll do green with green. So 5 times 2 plus 0 times 1. Now, you don't have to write out this entire thing every time. You'll see you can find out what you're comfortable doing. So you can do it in your head, or you can maybe just do You can do the products in your head and then add it up after. However you do it is fine, as long as you find an efficient way to do this without making any mistakes. So now if we go through and we simplify, we should end up with -9, 1, -4, 6, and -15, 10. So it's going to be that same process every single time. All right, so go ahead and pause the video and give this problem a try. Okay, so for your product, you should end up with -130, 2, -4, and 112. So remember, multiply, 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 and add up those terms. Okay, let's try one more together just to get a little extra practice. So let's check to make sure we can multiply them. Here we have 2 rows and 3 columns, 3 columns and 2 rows. So we can multiply them, and our resulting product will be a 2 by 2 matrix. So I'm going to do the multiplication in my head, but we'll add the sums in the second step. So 1 times -2 is -2, plus 0, plus -3. So I went across and down for the first row and the first column. And now let's do the first row with the second column now. So we'll have 1 times 4, and 0 times 0, and 3 times 1. Now second row, first column, we will have -4, -1, plus 2. And then in our second row, second column, we will have 8 plus 0 minus 2. So if we add those all up, we will get -5, then 7, and then -3 and 6. So there you have it. Okay, go ahead and pause the video and give this one a try. Okay, so you should end up with -3, -22, 310, and -510. So just a quick example here of what it looks like when you can't multiply them together. If you look at that first matrix, it's a 3 by 2. If you look at the second matrix, it's a 3 by 4. So since these two numbers do not match up, you cannot multiply them, and we just say undefined. So properties of matrix multiplication, some of these will look very familiar, but what's important to note is that you have to maintain the order of your matrices. You can't just switch around A times B or B times A, because as you know, you might end up with an answer for A times B, and then you might end up with undefined for B times A, depending on what the dimensions of your matrices are. But some of the products still, or some of the properties can still be used. For example, you can still distribute, but notice, if you're distributing from the left, A needs to be on the left when you distribute it to your other matrices. But if you distribute from the right, your C matrix needs to be on the right, because that order does matter. And if you're multiplying, you're doing matrix multiplication and scalar multiplication, you can multiply the scalar after, you can multiply it to either one before the matrix multiplication, and it doesn't matter. Okay, so one thing that I want to just introduce today, which is going to be very, very important when we start talking about the inverse of a matrix, is what's called an identity matrix. So we've actually worked with these. This is when you have ones going across diagonally, and then you have everything else zeros. So you might notice that this looks just like our result when we do Gauss-Jordan elimination. So this is called an identity matrix, and the reason why is because it's a multiplicative identity, meaning that when you multiply this identity matrix to any matrix, it will stay the same. It will maintain its identity. So note that if I have a matrix like this, the dimensions of my identity matrix need to match. This will only work with square matrices. So if I multiply my matrix by the identity, my matrix stays the same. But the nice thing is the order shouldn't matter. I can multiply the identity by the matrix, and the matrix stays the same. So you could do A times I equals A, or I times A equals A. So that's the definition of an identity matrix. So just wanted to touch on it today. This is what they look like, and of course you could adjust it to add in extra columns and rows, but we're going to use them very heavily in the next lesson when we talk about the inverse of a matrix. Okay, the last thing I want to talk about is an application of matrix multiplication. So you may be wondering, oh, why would I ever want to multiply two matrices together? Well, here's a good example. Here we have two equipment lists for a women's softball team and a men's softball team of how many bats, balls, and gloves they have. And we know how much each of those items costs for one, so they want to know what's the total cost of equipment for each team. Now, obviously, this is something that you could do pretty easily by hand without using a matrix, but the idea is that using a matrix would come in handy if there are maybe 1,000 or 1,000,000 different products that maybe a company is buying, where it would take a very, very, very long time for you to go individually and multiply and add them all up. So you can use matrices here to kind of speed up the process. So the first thing we're going to do is we're going to create an equipment matrix. So we're essentially just going to maintain that same order. And this lists how many of each product we need. Now, what's important to note is since the order of our products here is bat, balls, and gloves, we need to maintain that same order when we create what's called a cost matrix. So our cost matrix is going to end up being a horizontal matrix, and the costs for bats, balls, and gloves, respectively, is 80, 4, and 90. So I see that this is a 3 by 2 matrix, and this is a 1 by 3 matrix. So I can see that I'm going to need to multiply these in a specific order, just to make it even possible. So I actually need to do matrix C times matrix E. If I do E times C, the dimensions don't match up and you won't be able to multiply. So the order that you multiply in is extremely important. So if you do your multiplication, and remember we can expect to get a 1 by 2 matrix, we end up with 2,490 and then 2,882. So now we need to interpret what these mean. So you can see that in our original equipment matrix, the first column represents the women's team. The second column represents the men's team. So it's going to hold true for this as well. This is going to be the cost for the women's team, and this is going to be cost for the men's team. So for the women's, the cost is $2,490, and for the men's, the cost is $2,882. So that's just one example of an application where you would want to use matrix multiplication. All right, that's all for today. Thank you for watching.